Well, that's fun because I missed a day that used like Dexter's algorithm. And the internet of my new place is spotty at best. So I got like 2 seconds into the life and I was like, nope, I'm not going to use it for today.
I decided last night and I was working like all the 4 days, 5 days, Black Friday.
Yep, same here.
Same here. Do you guys work in retail stores?
Yes, I
get Fred Meyer's.
Yeah, you know how it is.
Oh, I got
4 hours for us.
Macy's.
I got 8 hours of sleep
Oh.
the last 2 days.
Yeah, same story.
I was looking scheduled for 3 2 so
Like,
all of that happened before I came in.
3 a.m. in the morning, next day.
Yeah, I worked Thanksgiving night.
I like how organized the papers are on this Clark podium.
Well, and
Easy
people
to understand
change them around currently without knowing what they're doing.
We would never do something like that.
It's like most of the stuff
And
you
to plug
can't
into
afford.
random spots.
The funny thing is that it's mostly only professors that use that. Computer science ones know well.
Yeah.
And engineering.
Does engineering bleed over here? I thought they only had that one room. Oh.
You should know better than to let a computer scientist touch hardware. Rule 1.
That's why I ask my wife anytime I need to do computer stuff. Like, honey, you're the hardware one.
Yeah.
Your turn.
Well, that'd be like getting a physical therapist to do neurosurgery. It's like it's not the same.
But it's all just computers, right?
All right. Any questions up to here?
On the first homework question with the president's graph,
Mm-hmm.
That one threw me. I don't think I got it right.
yeah, same here. So, the majority are linking the ones to, are dependent on the other one. Because I looked on the example online,
Mm-hmm.
and they had to say like for S1 was X equals something 2, let's just say. That it was linked to every single node, even though not every single node had X in it.
So here's what I would do. So set of statements.
My question is, are these statements sequential?
They're supposed to be executed sequentially.
Alright.
Right, so S1 is the first statement. It doesn't depend on anything. S2 is also independent of anything that comes before it. But S3 depends on S1. It depends on X, which is S1. So until S1 is done, we can't do S3. But once S1 is completed, S3 is ready to fire. S4 depends on 2 and 1, so we need both of these before we can do S4. S5 depends only on Y, which is S2. And then S6 depends on X, which is S1, and K, which is S5. So S6 would come like this.
Okay, that's fine and dandy. Go ahead and change that S4 over to an X equals Y plus X. And then how does that change the graph? Because now you've got 2 statements that change X. And
Sure.
then if you get down to say 6, you have to link both of those as
Not
precedents?
directly.
You just like
So S4 gives the value of X. S5 is still
Because
just
that's
dependent on 2.
sequential. Right.
So S6 depends on X, which is set up by S4, as well as K, which is S5. So
So it wouldn't,
if you draw it like this, you can analyze it and see that you can't do S6 until you've done S2, right? And you cannot do S6 until you've done S1. But the immediate dependence here is on S4 and S5.
That's where the examples are confusing me, because.
Because they were doing arrows all the way down?
Yeah, they were
Yeah.
like, and it was just like, I mean, if it even was even remotely connected, it was made every node. I mean, that kind of makes sense, because you
Yeah.
set it up so where S1 can happen and then S6 can happen.
And that sounds like it's kind of redundant.
Yeah.
Like it's displaying information that's already available in here, just not immediately
Well,
presented.
I could see it being useful to show that, just because, like, you know, maybe you want to do S6 before you do S4.
Mhm.
And it shows that you can do it, because
Right.
you do not need S4, you just need X.
Right. Yeah.
I must have missed you saying that they're sequential, when you first mentioned them like, 2 weeks ago.
Okay.
Because I ended up drawing it so where, some of them were dependent on later things,
Mm-hmm.
which don't work.
Yeah.
It's also much easier to visualize when it's drawn, like you've drawn it just now instead of like a circle,
Right.
which threw me also.
Okay.
Yeah, mine kind of ended up looking like if I actually drew it right, it was almost like a square.
Yeah, I mean, if you just label these like this, then you get, something like that, and this, and then this depends on Y, and then this depends on X and K.
Oh.
And it's the same graph, right? It's just drawn in a way that things are at different positions, but they're identical graphs.
That's actually much easier to parse even though you've got like so many things running over each other.
Yeah, it's easier like this.
I think it's
It
pretty
helps,
clear.
it helps tie in the sequential nature
Yeah.
of it,
Okay.
especially when you put it together by drawing the lines down.
Yeah. So what I've done here is I've sort of laid it out in time, right? This could be time step 0, time step 1, time step 2. Assuming each of these take a single time unit to execute. We can do these at T0, these at T1, we can do this at T2 by putting a different level for each.
Well, this one won't be graded, right?
A. It's all graded, man. It just doesn't necessarily go into the number.
Other questions? I got stuff at 4.
4.
Making a directed graph out of the adjacents
Draw a graph for the adjacency matrix.
matrix. It might be,
So what were you stuck on?
because I don't know how to make, I don't know. how
That
to-
looks directed because it's not symmetric.
Okay.
So let's do an example.
Well, when you're doing that, do you pick do it each row at a time or each column at a time? Or am I?
There's no time component in the direct.
Well, not time, but I did my rows.
Oh.
So in this case, like node 1 would be up.
Oh, I see what you mean,
Node
yeah.
4.
Oh, yeah, I see what you mean. You have to make that distinction, actually.
So you have to decide what's from and what's to. So I'm just going to do from on the rows and to in the columns.
Can I make a quick edit to my homework?
Why? What did you do?
I didn't add the from to.
So how did you do it?
Well, I mean, I just didn't write it. I did it exactly like that.
Okay, that's fine.
Alright.
Yeah.
You
So
just have to make that decision.
Yeah.
so we have an edge in this case from A to D, and from B to A, and B to C, and D to D.
So they're not exactly errors, they're lines with the thing in them.
They're arrows, but if I draw it down here, they start to jumble into each other, like right here.
Right.
So
Okay.
on Mondays, I draw them in the middle.
In the homework, there was one situation where one of the letters didn't have anything linking
That's possible.
away from it at all,
Yeah.
which is still solvable.
Yeah, sure.
Well, in this case, and with this one, if you did it reverse, like from columns to rows, then you would have B not, would be disconnected.
Yeah, that's
I mean, I could
exactly
do
it.
this.
But in actuality, it's not disconnected. All it means is that you can't either leave or go to it.
Right, but if I do this, alright, now we've got a disconnected graph. We've still got a vertex C, but there's nothing going to or coming from it.
So that means that one edge you erase would be considered a bridge, based on what I was reading.
A bridge.
I was doing it off reading, and so you said any single edge you can erase or like delete is called a bridge. If it, you know, if you delete it, it becomes a disconnected graph.
Okay, I like it. Yeah,
In the programming assignment, we considered all edges to be two-way, right?
yeah,
Okay,
I
good.
think so.
Well, it's undirected.
Yeah, it's undirected, so it's two-way. Good. All right, so we were talking about vocabularies. No, we were talking about sentences, syntax versus semantics. So the happy pink mathematician jumps quickly.
You mean the pink bacon quickly runs?
Yeah, the pink bacon quickly runs. All right, so so how can we specify syntax? So let me give you some definitions of vocabulary. Which we'll call is a finite, non-empty set of symbols. We can define a word over V, and sometimes we'll call it a sentence, but usually I'll stick to word. A word over V is a finite length string. Of symbols. There are elements in V. So for example, our vocabulary could be ABC. So those are our symbols, and that could be a word. That's also a word. Okay, finite length string of elements, so we can repeat symbols. There's a special string called lambda. That's the empty string. It's a string consisting of no symbols. It's not the same as the empty set. An empty set is a set, this is a string. But it contains no symbols. V star is the set of all words over V, including lambda, the empty string. This is the same star you use in regular expressions, by the way.
So is V star like the subset then?
V star is a collection of all words over the vocabulary. So if this was our vocab, V star would include the empty string A, B, C, A, B, B, C, B, A, and so on.
So it's an analog to the power set.
Analog to the power set.
I'm sorry, yes, I meant the power set.
Yeah, yeah.
Sorry.
Okay.
Yes, good call.
If our vocabulary consists of the single symbol X, V star consists of all of these. The lambda, the empty string, X, 2 X's, 3 X's, 4 X's, and so on. In other words, 0 or more occurrences of that symbol X. That's where the star from regular expressions comes from. So you've been doing this stuff already. All right, so now we can define a language over V is just some particular subset of V star. So we start with a vocabulary that's a set of symbols. We can define words, which are finite length strings of those symbols, including the 0 length empty string. And we can define V star, which is a collection of all words over that vocabulary. And then we can speak of a language over V, which is some particular subset of the set of all words. Okay, and it's a pretty good analogy to human languages. Our vocabulary would be the letters. Our words would just be collections of letters. V star would be the set of all possible combinations of letters. And then the language is those combinations that we choose to say are part of the language, which for us would be things that are actually words that we think of as words, the cat, dog, and so on. All right, so we'll hold those. So the question is, how do we specify a language? So, how to specify a language? And again, we're just talking syntax. We're not talking about the meaning. We're just talking about the syntax. How do we describe what constitutes a particular language? And there's at least 3 ways. The first is to simply give you a list of all the words that make up that language. And that's pretty straightforward but cumbersome, particularly since in most cases you have an infinite number of words. So a second option is list requirements or rules for a word to be in our language L. So list all words in L. The second approach would be to list requirements for a word to be in L. For example, it has to have an even number of symbols, it has to begin with a 0, and it has to end with 1, 1. We could do that. But that's hard to make systematic. And in some cases, it's hard to actually describe a way to test a word and see whether or not it's in this language. So our approach is going to be to describe a grammar for our language L.
Is grammar a singular noun? Is grammar a singular noun? What do we describe the grammar?
Yes, it's
I think we can have multiple grammars.
Oh.
I wouldn't swear to it.
This isn't even supposed to be a sentence. Those sentences aren't even supposed to fit by this, and then we're,
Yeah.
it's not even an example. It's just, that's a sentence.
Yeah. right, so we're going to talk about grammars for the next couple of days.
When will we begin using the grammars?
We're using them now. That was not a word. There's a word in my grammar. So this is a four tuple. So we're going to describe this thing called a grammar that's going to tell us which words are in our language. So a grammar is a four tuple, V, T, S, and P. All right, any guess what V is? Vocabulary, good. The set of symbols from which our words are composed. T is the set of what we call terminal symbols.
Punctuation.
Could be punctuation. Punctuations would generally be terminals. It's a subset of our vocabulary, though. It's some particular set of symbols that we just define to be terminal. We'll see what that means.
So that means that punctuation, including spaces and periods and apostrophes, are all included in our vocabulary.
Yes, yes. Yeah, the vocabulary is a superset, every symbol that can make up your words. T is the subset of those that we'll call terminals. S is called a start symbol. And P is a set of production rules.
The start symbol is also a subset of V, right?
I think it's an element of V.
But it is a subset, right?
Yeah,
Okay.
but it's not a set of symbols. I think it's just one symbol. This will be enough for us to fully describe a grammar of a language. Okay, so let's try some examples. So our vocabulary is going to have 5 symbols, little a, b, big A, B, and S. Our terminal symbols will just be little a, b. Our start symbol will be S. And our production rules will be as follows. So there's one, S goes into big A, big B, little a. A goes into 2 big B's. Big B goes into little a, B. And A, B goes into B. There's a grammar.
Wait. You have 2 variables in the left there. A, B goes to B.
Yeah.
So A, B is different from A or B.
It's an A followed by a B. Okay, so what does all this mean? This is basically saying that if you have this collection of symbols, you can replace it with this collection of symbols. So if I have an S, I can replace it with ABA. If I have an A, I can replace it with BB. If I have an A followed by a B, I can replace it with a little b.
You can replace S, doesn't mean you have 2 start symbols,
S is my only start symbol.
but you can replace, isn't S equivalent to ABA?
It means I can replace it with ABA. but that does not make ABA a start symbol.
Do you have to replace it?
Your goal in doing this is to come up with a set of words. And the terminal symbols are the things that make up your words.
Oh, so it has to.
So we're trying to take these production rules, start from our start symbol, and come up with words that contain only things in our terminal set.
But for example, if you were to start with the start symbol goes to big A, big B, little a, and that can go use either the second or the third rule or the fourth rule. I'm sorry, the second and third or the fourth.
Okay, so let's try this. So we start off with an S, we come up to ABA. So one thing we could do is we could take AB and we could just replace that with B, and we get this word, BA. And there's no production rules for changing either of these into anything else. So that's a word in our language. But we could also have said S goes to ABA. And we could have taken this first A and replaced it with two B's. So we get BBBA. And the only thing we can do here is replace that big B with a little AB. And the only thing we can do here is the same thing. And that last B can become another ABA. And so there's another word that we can get in our grammar. And I believe those are the only words we have.
It's very primitive language.
Yeah. Maybe it's yes, no. Maybe it's bacon or salad.
So it could be a yes, probably.
Yeah.
So wait, can you stop? Like, can you just take the middle one, like B, 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 A?
Technically, yeah, that's a word in our grammar, but we want to get it down to things that are only in our terminal set. Okay, these are, if you like, they're intermediate symbols that we use to get a hold of these production rules. But our goal is to reduce everything to something comprised of elements from our terminal set.
I guess one complication is next, so with our English, it would be your vocabulary would be the same as your terminal symbols because of your alphabet. Like your alphabet is in your.
Our vocabulary might include things like noun, verb, predicate. And you wouldn't leave a sentence as the adjective mathematician. You would want to change that into one of our terminal elements like the large mathematician. And to some degree, coming back to English can help, but to some degree it's going to make less and less sense. But I think it works in that case. All right, so that's an example of a grammar. And another way we could analyze this is to say, here's an S. S has got to change into ABA. But we could take AB and just change it into a B. Or we could take our A and change it into a BB. And then we could take our B and change it into an AB. And we can start making trees of these things. And if we had some other way, like if we had a rule for BB changing into something else, we could put another branch down here and show what happens when we use that production rule. So each application production rule can...
If you're going to get the same word, we are just picking one, right?
If I had a rule for BB, I would follow it down here. It might take me to the same word, it might not. But this is a way to sort of deal with the recursion that comes in trying to apply these. And the fact that you might have more than one way to apply your production rules at some point.
Wouldn't the triple BA actually have like 3 different trees where you each replace each different B? Is that considered different or not?
You could do that.
Does the order matter?
Yeah, you could do that. We could do B, A, B, B, A. In fact, you probably want to do that.
Well, then you should also have a separate, a third branch off the ABA for if you change the B before you change the A. You know, because what if you change your B to AB? It would wind
Yeah,
up,
sure.
It would wind up at the same spot, but
No, that's fine.
yeah, it's still another change.
B, A, and then
And then your A is 2B, becomes BB.
Yeah, okay.
They could end up in the same place.
Yeah, but if you were doing this programmatically, yeah, you probably got on all those different branches.
So you'd wanna explore every
Yeah.
option sequentially? Okay.
Yeah, and possibly do some pruning along the way, like once I got here, I might recognize it from this branch and only traverse one of them.
So I wonder, some of these you might come to the word faster if you start changing in different orders.
Sure.
So I wonder if there's some way that you could like edit your production rules based on how fast you can get to specific words.
You might be able to. Technically, it's a set, so it's unordered. But if you start coding it up, you might find some ways to generate some statistics on these and decide which way to branch down first. That's probably doable.
If you had redundant rules, could you reduce them? Like,
Redundant production rules?
Yeah.
Yeah, you probably don't want redundant rules in there.
just end up reducing.
Someone in here is going to invent the next Google, I can tell. I just get that feeling. All right, let's try another example.
Is the star symbol a word itself?
It's just a symbol.
So we are not
It's
using
part of the vocabulary. And it always seems to be S in my example. So our terminal symbols are going to be 0, 1. Our start symbol is S as usual. And our production rules. So S can go to 0A, S can go to 1A. I better tell you what A can do. A can be 0B, A can be 1B. Nope, can't. A can be 0B. B can be 1A, or B can be 1. So what do our words look like? They'll definitely look like binary. But will it look like all binary?
It started with 0, 1, and then it goes.
So let's start with this one. So 0A. And A has got to be a 0B. And B is either a 1 or it's a 1 followed by an A. So if it's just a 1, then we've got 0, 0, 1. If it's a 1 followed by an A, we've got 0, 0, 1, A. And A is 0B. And again, B could be a 1. Or B could be a 1A. So it's 0, 0, 1, 0, 1A. And A is 0B. And B could be a 1. Or it could be 0B. And you can start to see a pattern here. it's basically going to be 0, 0, 1, followed by 0 or more occurrences of 0, 1. Or if you like. Right, like that. So that's from our first production rule. We also had a different production rule where it was a 1 followed by A. And that's going to 1, 0, B, and it's either 1, 0, 1 or 1, 0, and that B can become a 1A, so it'll be 1, 0, 1. And so it could also be a 1, 0, 1, followed by any number of 0, 1s. So we have an infinite number of words described by this grammar, but they fall into one of these two patterns, either a 0, 0, 1 or 1, 0, 1. Or if you like, it's a 0 followed by one or more repetitions of 0, 1. You got a question?
Oh, I just realized that you can basically go backwards and has any word as part of the language.
Mm-hmm. Yes. That's not always straightforward to do.
Yeah.
But yeah, you can tell whether something's part of the language by using this.
Also, another production rule being back to itself. So like A equals, or that goes to 0A. As long as you have another one.
Yeah, you could. I don't know if that's considered officially legal, but certainly we could say B goes to 1, 0, B.
Yes.
Right.
Then wouldn't that never end?
Well, it will end because you have B could also.
Or B could go to a 1.
Oh, I see. Yeah.
Now that you only had it like if we did with A.
It was only that, yeah.
Yeah.
I got you.
So basically, the production rule is just a substitution.
Basically, yeah. Yeah.
Do you have a production rule that has a definition for a terminal symbol? So one
Definition
goes
for
to 1A.
No, terminals mean that they don't change into anything else. All right, let's try one more. So three symbols 0, 1, and S, terminals are still 0, 1, simplified production rules. S goes to 1, 1S, or S goes to 0. So what are some of the members of our grammar?
A whole bunch of ones terminated by a 0.
How many ones?
Anywhere from 0 to infinity.
Someone else said something different.
Even number.
An even number of ones.
That's true.
Yeah. So certainly this is
Yes.
defined by this rule, but it could also be a 1, 1 followed by a 0, or 1, 1, 1, 1, and so on. So it's an even number of ones, including 0 ones, followed by a 0. So we can use grammars to start describing things like regular expressions. We can think of regexes as things that fall out of a particular grammar. But we can also construct grammars in order to describe particular patterns, particular sequences of characters. So for example, let's go the other direction. There's some grammar whose language consists of the following. The empty string, or a string consisting of n zeros followed by n ones. So it's either empty or it's 5 zeros followed by 5 ones. And we'd like to construct this grammar G that corresponds to this language. So our terminals will be 0, 1. Our start symbol can just be S. Our vocabulary will include 0, 1, and S. And it might need to include other things, or it might not.
You could never fully define the vocabulary from the language, though, could you? Because there could be something that you never use.
If you know that that's the language, you should be able to completely define the vocabulary.
So, what if in one of our other cases, though?
Well, no, it might not be unique. You're right.
Yeah, because you could have some C that you just never need to use.
Yeah.
But it's there. Okay.
And it doesn't give you a different language, but it's not necessary.
I mean, it's a trivial question, I guess, but.
So, how do we define production rules to give us this language?
Start off with S.
Okay, what should S change into?
That should change into 0, 1. Well, no, that's a terminating.
The first one is supposed to change to lambda because
Yeah, this has to be one of our production rules. That a sentence can just be, or S can just become the empty string. So that's certainly one of our production rules. But what about these other?
Could it be
0S.
Start with 0.
0S1, I would say?
Yes.
So then you would expand.
0S1 or 01.
Yes.
0S1 will do it.
Yeah.
Or 01. Oh, sorry. And then you turn it into the null.
Because I can change that S into the empty string and it just gives me 0, 1. Perfect. So that grammar describes that language.
or we can have lambda go to 0, 1, 0, 1 go to
You can't transform lambda.
Would that mean you should put lambda in your terminating?
It's an empty string. It's different. There's probably a way to say that. But
We also need more production rules to say that S can go to 0, 1, 0, right?
No.
0 is not part of our language, neither is 1. Our language is just the empty string or 0, 1, 0, 0, 1, 1, and so on.
And you want an equal number of zeros and ones for each one.
Yeah.
So we can't just have a 0.
No. So say for 2, what you do is put. You good? Right.
So that would be how we would derive 0, 0, 1, 1. Or we could transform this S into right. Yeah.
Can we say S goes to 0, 1, 0, 1 goes to 0, 0, 1, 1?
You don't want to change 0, 1 into something. Right, because zeros and ones are a terminal. If you have a 0, 1, it's just a 0, 1, but you can say something like 0, 1A changes into. Yeah, you don't want to do just this.
You may want terminals on the left side there, or
I don't think so.
Well, by definition, if they're terminals, they don't change anything.
If they're terminals, they don't change into anything.
I was thinking that's what we did in the second example.
This is a very inductive one.
We had S's, A's, and B's on the left. That second example. Big A's and big B's. Yeah, it's kind of inductive, it's kind of recursive. Yeah, probably a little more than a little recursive. Suppose we want 0 or more zeros followed by 0 or more ones.
And naturally, we can model this like algebra, where each character is sort of multiplied by others, so we can get exponentials out of that.
Yeah. I'm possibly abusing some notation here,
Just a little bit.
but my intent is to find a language containing the following things.
So, let's see here. We've got S can go to lambda, that's probably a given.
So yeah, any number.
And then we've got S can go to 0S, and S can go to S1.
That will get us a bunch of zeros, eventually followed by a single one.
But can't we just put more ones in there?
S equals 0. No, S equals 1.
You never have just S equals 1.
But you're going to need something else to get multiple ones here. But that's the beginning of it.
Why wouldn't that give multiple ones?
How?
Would S replace S1 with S1, or just like keep replacing S with S1?
Yeah.
And eventually make S lambda.
Let's see. So I could have S. That could be a 0 followed by an S, which is an S followed by a 1.
But why do you
Just
do
do
it that
S1
way?
again.
Oh, wait, no, this one. Because then you can make S lambda and you can have 0, 1.
Yeah.
Then you can do the same thing. So if
So
you make
this can become
that
S
S a 0 S.
1 1.
Oh, right, sure. I know what it is.
So that S can become. Yeah, maybe that does work.
Yeah, because I was kind of picturing it as you start at some state, which would be one of those S states, and then you're at that state and you can make a decision about what you're going to do given the characters that are present. So in this case we have an S present, so we can either go with S to lambda, S to 0S, or S to S1.
Right.
That's 3 options coming off that tree. We can do whatever we want with it effectively. Now, what I'm seeing here is that there is a limitation. We haven't guaranteed that there's at least one 0 or 1, which is
Yeah.
required. Or no, it can be greater than or equal to.
Yeah,
Never mind.
you
Never
don't
mind.
need them. This bothers me for some reason. I gotta check on that to see if that's kosher.
Why wouldn't it be?
Because the S is in the beginning on the right-hand side, and I'm thinking of it in terms of recursive programming and tail recursion versus not. How do you tell if it's an S followed by a 1? You call S to see if it's an S, and you're going to keep calling S, and you're never going to come back. You're just going to sort of descend forever down this.
You might lose the ones off the
Yeah, and there may be a rule about these production rules that says you need to have terminals in the beginning or something. I gotta check into that. But barring something like that, I think this works.
So
for that.
what you would need to do in this case is read to white space, right?
You need to introduce another symbol that you can use to get your hands on.
Like a terminating character.
Yeah, yeah.
Yeah.
All right, we're over time here. I'll dig into that, and we'll start from there tomorrow. It's a good point of discussion.